Very good evening, students. Today we are going to discuss about variable refractive index. So we generally know how to apply the Snell's law for a medium which has a constant refractive index. So let's apply the same Snell's law for a medium having a variable refractive index. We generally know something is variable means we want to use integration. Okay, let us see whether is there any need of integration in this variable refractive index. Let's see that. So generally we take only two cases, that is the refractive index varying along the x-axis and refractive index varying along the y-axis. So let's take the first case, that is mu is equal to f of x. That means the refractive index is varying along the x-axis. So let's see what's going to happen. So if you take the coordinate plane, I am just zooming the coordinate plane and considering the places at each x there will be 1 refractive index, and I am considering 1 slab for it. Yes, so at every place the refractive index is going to change at 1x. So let's imagine here it's x1, then the refractive index in this medium will be f of x1, x2 f of x2, x3 f of x3. So now let's see how to do this problem, and generally what we need in this type of problems is the refractive index is varying. Now they will ask us in what path the light is traveling. So it's generally what is the equation of the path of the light. Imagine the light has entered like this. Now if the refractive index is varying along the vertical line, let's have a normal called optical normal. Optical normal will be exactly perpendicular to all the slabs. I am using the word slabs because I am considering this as a infinite number of slabs where every slab refractive index is varying. So when the ray has entered exactly normal, means it is making how much degrees with the normal? That is 90 degrees it is making with the normal. So from here how the ray is going to be? Imagine it's going to be bended like this. So now what the thing we require is, what is the equation of this ray, or in what path it's going? Is it a parabola, or is it a ellipse, or is it a hyperbola? What path? So let's consider at one instance, let's take this point where this value will be x. Okay, if you consider a tangent, if we consider a tangent at that position and consider an optical normal, this tangent is going to make an angle theta. So if we extend the tangent carefully, same angle theta it is going to make even with the x-axis. That means the slope of the tangent is going to become tan theta. Till here it's fine. Now slope is nothing but dy by dx. Okay, now let's apply the Snell's law. See how many our slabs are there. Our Snell's law can be applied from the initial position to the final position. Whatever happens in middle, we really not worried about it. See, imagine there are plenty of slabs. A ray entered like this and exited like this. So we can just apply Snell's law here and Snell's law here. That's good enough. We need not really worry about what happening in the middle. Let me just erase the thing. So now the ray has entered here with 90 degrees. Now it entered this slab at theta. So let's apply Snell's law. It's coming from air. So 1 into sine 90 is equal to, here the refractive index is going to be f of x. F of x into, what is the angle it is making? With the normal it is making an angle theta. I think it's very clear. So now the sin theta is going to become 1 by f of x. Okay, and one more very important point what we know is, just before we got that, tan theta is equal to dy by dx. The slope of the curve at that point x is nothing but tan theta. So we can get this tan theta value from this equation. Sin theta is equal to 1 by f of x. So tan theta is going to become 1 by root f of x whole square minus 1. So now we can apply integration over here to get the value of y. Thank you. This is how we solve the problems when the refractive index is going to vary with x axis. So please see my next video how to do the problem when the refractive index is varying along y axis. Thank you.